Welcome to JCB EduBuild Solutions. To all our engineering specialists and board reviewees joining us today, let's dive straight into the mechanics of sizing water systems. The physical challenge of plumbing design comes down to two inescapable forces, gravity and friction. As water climbs through a high-rise, it bleeds pressure. The higher it goes and the more pipe it scrubs against, the slower it moves. The ultimate objective for the plumbing engineer is to guarantee that the highest and most remote fixture in a building operates at code-compliant pressure during absolute peak demand. Achieving this requires you to strike an exact mathematical balance between two variables, the system's total demand load and its permissible friction loss. We determine this balance through a strict three-phase calculation workflow. First, we determine the peak volume demand. Second, we evaluate the static pressure lost to gravity. And third, we factor in the dynamic friction loss generated by the pipes themselves. Mastering this specific sequence provides the mathematical bedrock for safe plumbing design, and executing it perfectly is a requirement for anyone pursuing their professional board certification. Our model is a 4-story office building. We require 4 given variables. First, starting street main pressure is 379 kilopascals. Second, a vertical climb of 13.7 meters to the highest fixture. Finally, the total developed pipe length is 60.8 meters, and we use flushometer valves. Street pressure, elevation, pipe distance, and fixture type. You must gather these 4 inputs before attempting to utilize any sizing charts. Phase 1 is calculating the demand load. Engineers do not size pipes based on a raw count of toilets and sinks. Instead, they assign water supply fixture units, or WSFU, to account for the mathematical probability of multiple fixtures being used simultaneously. This is Table A1, the demand weight of fixtures. We use this to find the unit weight of components. If we look up a flushometer valve water closet in a public setting, it carries a heavy WSFU rating of 10. By multiplying that unit weight by the total number of identical fixtures in the building, we establish the aggregate fixture units for that specific branch. This table calculates the fixture units and estimated demands for our 4-story office building example, detailing totals for water closets, urinals, showers, lavatories, and sinks. Summing those rows gives the absolute peak load for the entire building supply, 1,866 fixture units. Remember this critical rule: WSFU is a probability metric, not a flow rate. To size a pipe, we must convert that abstract number into liters per second. This estimate curves chart allows us to make that precise conversion. Notice curve 1. It is applied strictly to systems dominated by flushometer valves, accounting for their sudden, high-volume surge. To plot our system, we locate 1,866 on the horizontal axis, trace straight up to intersect curve 1, and read the resulting flow rate on the vertical axis on the left. By navigating the table and the chart, we have translated the architect's building layout into a concrete engineering requirement. Our peak demand is exactly 19.7 liters per second. Phase 2 shifts our focus from water volume to water pressure. We need to calculate our pressure budget, identifying exactly how much of the starting street pressure is immediately lost simply fighting gravity. This formula determines the remaining pressure available for friction loss. We begin with 379 kilopascals, the available daily service pressure delivered by the city main. Next, we subtract the elevation penalty. Water loses approximately 9.8 kilopascals for every meter of vertical climb. We multiply that by our 13.7 meter elevation. Next, we perform a second subtraction to reserve the minimum operating pressure for the highest fixture. Because we use flushometers, we must reserve a substantial 103.4 kilopascals at the endpoint. Completing the math leaves us with a final result of 142.3 kilopascals. This is the remaining pressure available specifically to overcome pipe friction. That 142.3 kilopascals is a strict budget. Every millimeter of friction generated by the pipes, valves, and fittings must fit within this margin, or the top floor will fail to operate. Straight pipe walls cause predictable friction, but every time water hits a valve or a corner fitting, violent turbulence creates severe pressure drops. Phase 3 accounts for this dynamic loss. This is Table A2, the allowance in equivalent length of pipe. Engineers use this matrix to assign fittings a virtual distance in straight pipe to account for turbulence. For example, placing a single 90-degree standard elbow on a 50.8 mm pipe generates the exact same friction as forcing water through an additional 2.1 meters of straight pipe. To establish the final permissible friction loss standard, we take our remaining pressure budget and divide it by the total developed length, which is the actual physical pipe distance, plus the equivalent lengths of every fitting in the line. This final equation multiplies our reference length of 30.4 meters by our pressure budget, then divides by the total developed length. The result is 71.1 kilopascals per 30.4 meters. This value of 71.1 kilopascals per 30.4 meters establishes the maximum allowable friction the system can tolerate. By cross-referencing this limit with our 19.7 liter per second demand, the engineer finally determines the exact diameter required for the main supply pipe. There is a final hazard to avoid. If an engineer uses that same maximum permissible friction loss to size the branches on the lower floors, it will create a systemic imbalance. Lower floors naturally have higher local pressure because they are closer to the main. If sized uniformly, those lower branches will draw water too easily, starving the upper floors of volume during peak demand. Engineers solve this through deliberate system balancing. They intentionally select smaller pipe sizes for lower branches to increase local friction, or they install throttling valves to artificially restrict the flow, equalizing the system pressure from bottom to top. Let's summarize the calculation rules you must lock in for the exam. Rule 1. Always convert water supply fixture units into actual liters per second. Never attempt to size a pipe based on raw fixture unit counts. Rule 2. Memorize the physics. The static elevation penalty is 9.79 kilopascals of pressure lost for every single meter of vertical climb. Rule 3. Always calculate equivalent lengths. Ignoring the turbulence generated by valves and fittings guarantees a mathematically undersized failing system. This demand-friction balance is the specific calculation that distinguishes a code-literate engineer. Mastery here is required for certification and is the only way to ensure a complex plumbing system operates as intended.